this computer. Okay, so it's my pleasure to introduce Goncalo Oliveira from IST Austria, who is coming with us in our first analysis geometry seminar of the semester. In his talk is about special Lagrangian and Lagrangian mean curvature flow.
Okay, thank you very much for the introduction and for the invitation to speak. It is a pleasure to be virtually in Chile giving this talk. So I'm first going to motivate or say more or less what the topic will be. And so let us start with the sympathetic manifold. So that's a 2n-dimensional smooth manifold equipped with a non-degenerate closed two-form. So omega is a two-form that is closed and non-degenerate, meaning that its top exterior power never vanishes. So it is in particular a volume form. And L is an half-dimensional submanifold and is going to be a Lagrangian. So it's a Lagrangian submanifold. So Lagrangian simply means that if you pick the sympathetic form and you restrict it to L, that vanishes. And if you are used to thinking of sympathetic manifolds as generalized phase spaces for mechanical systems, maybe you can think of Lagrangian submanifolds as generalized configuration spaces for mechanical systems. So if sympathetic manifold keeps track of coordinate and momenta, then a Lagrangian submanifold you can think as keeping track only of coordinates. And in sympathetic geometry, it is natural to think of Lagrangian submanifolds up to an equivalence relation. So you say that L, yes, please? Yes.
If you're thinking of the cotangent space, a Lagrangian submanifold would be what?
Sorry, say it again.
If you are thinking of the cotangent space as a sympathetic manifold, right, in classical mechanics, a Lagrangian submanifold would be what?
So an example, let's do an example. If you take M2n to be the cotangent bundle of some Riemannian manifold Q that is n-dimensional, okay? Q, sorry, not Riemannian, so some smooth n-dimensional manifold with the standard sympathetic form, which is d theta, where theta is the canonical one form. So that's the tautological, usually called tautological sympathetic form. Then an example of a Lagrangian submanifold is, for example, the zero section. So Q inside T star Q as the zero section is a Lagrangian submanifold.
And a less trivial example, could you give another less trivial example? Or there are
so another example, so this is somewhat trivial, but it's very important. I can say it in a second why. But another example in the same space would be a fiber. If you pick a point in Q, and if you look at pi minus 1 of Q, where pi is the projection, that is also an example of a Lagrangian submanifold. So this is a Lagrangian submanifold. Another example in the same setting is if you pick on Q a closed one form. So let's say that let alpha be a one form on Q that is closed. For example, if you pick D of a function, one thing you can do is to look at the graph of alpha. So that's a submanifold of T star Q. And the condition that it is closed is equivalent to this being Lagrangian. Okay, so these are 3 examples of Lagrangian submanifolds of the cotangent bundle. And of these, the more important is this one, because there is a theorem of Weinstein that says that locally, any Lagrangian submanifold looks like this, looks like the 0 section in a cotangent bundle. Okay, so this is the local form of any Lagrangian submanifold is modeled on this example that I've put it inside the square. Okay, are these examples, do they help you?
Yes, the third one is the one that you see in some papers, right? From laws and stuff like that.
Sorry, can you say it again? I couldn't listen very well.
But the third example is the one that you usually see in some papers also. I mean, the local model, also the third one that you proposed.
Yes, so the third one, once if you pick a local model for a Lagrangian as in the one in the square, if you want to look at some Lagrangian submanifolds that are close to it, then you can use the third example to look at some Lagrangian submanifolds that are close to it and which are graphical over the 0 section.
Thank you. I mean, maybe you have to be aware that we're not expert on sympathetic geometry, right? Most of the people.
That's fine. That's fine. It will be. I will be gentle in the way I will introduce things. But if you are not too familiar with sympathetic geometry, maybe in this example you can sort of disregard these two and just keep the first one in mind. Okay, it will not be too important to know many examples in higher dimensions. I'll give you all the examples that you need to follow the talk. Okay, so maybe forget these the second and third examples and remember the first. But even if you don't remember it, it will be okay. Okay, so the next thing I want to say is that usually sympathetic geometers regard Lagrangians to be equivalent to which, so there is an equivalence relation inside the space of Lagrangian submanifolds. So they are called equivalent if they are Hamiltonian isotopic. And I'll explain what this means in some examples, okay? If I spell out the general definition, it will not be very illuminating, so I will go through an example for you to get an idea of what this means. And I'm going to denote by L inside straight brackets to be the Hamiltonian isotopic class of a given Lagrangian L. Okay, so it's equivalence class under this equivalence relation. And the natural question that appears is whether there is a best or canonical or even just interesting, so it's a very vague question, representative of a given equivalence class. So if I give you this equivalence class, can you find a very canonical or very interesting representative of it? Okay, so that's the main question that this talk will be concerned with. And I'm going to go through an example in order to motivate the answer that I'll propose in the talk. Okay. So the example we will see is going to be the two torus. Okay, so you can think of R2 mod Z2. With omega, the sympathetic form is the sympathetic form that descends from R2 is dx wedge dy. Okay, so we can think of R2 using the square model. Maybe let me make it here. Of the two torus as using the square model of the torus. Copy. We try to paste this. So, oops. Okay, that worked. Okay, that worked also. Okay, so I have here three squares. So there's three two tori. Okay, so I'm going to identify the sides like that. Okay, that's a torus. And I'm going, and in 2 dimensions, remember the condition that a submanifold be Lagrangian. So a Lagrangian is going to be 1-dimensional. And the condition that it be Lagrangian is that omega restricted to L is equal to 0. But omega is a 2-form and L is 1-dimensional. So this is always true. So, so any curve is a Lagrangian submanifold in 2 dimensions. So any curve is Lagrangian. And I'm going to draw here some Lagrangians that are diffeomorphic to a circle. So the first example is going to be a straight line like that. Remember that this point here is identified with that point, so that's a circle. Another example would be something that starts like here, another straight line like that, and ends up here. So it is going to be L1, L2. So that's a straight line. Remember, all the corners are the same because I'm identifying the sides, the opposite sides. So this point here is the same as that point. So that, again, that's a circle. And now I'm going to do another straight line, but with a lower slope, like that. It goes here to the middle. Now this point is identified with this point, and I'm going to continue it in this side, and then it arrives at this point, which is the same as that point. So I've now closed it. So I have here 3 examples of Lagrangians, and I'm going to draw some other Lagrangians. So other curves, L1 prime, L2 prime, and L3 prime, like that, okay? And the condition that they be Hamiltonian isotopic is that the signed area between them vanishes. Okay, so by the signed area, I mean, if you look at each of the pictures I've drawn, for example, here, the area in yellow, where the yellow curve is on top, always needs to be the same as the area in blue, where the blue curve is on top. So I'm now going to draw the area in blue, where the blue curve is on top. And these areas need to be the same. So that is the condition that they be Hamiltonian isotopic. And now, so in each of these pictures, you have examples of 2 different Hamiltonians, 2 different Lagrangians that are in the same Hamiltonian isotopic class. So which one is the best representative in each case? And the answer that I want to motivate is that the best representative are the straight lines. Of course, in order to say what a straight line is, I'm also using the notion that I have a metric there, which I'm somehow thinking of implicitly. But so now, how do I correct? So now there are 2 questions that I pose. If you agree that straight lines are a good candidate to being the best representatives of an Hamiltonian isotopic class, then the 2 questions is how to characterize straight lines and how to deform a given Lagrangian to a straight line. Okay, so first, characterize straight lines. Okay, so let's try and characterize them. So I'm going to pick a complex valued 1 form. That's basically dz. Z is x plus iy. Okay, so that's a complex valued 1 form. And I'm going to parameterize a Lagrangian using arc length. So Lx of S, Ly of S. Okay, that's a parameterization where S is the arc length parameter. Okay, so S being the arc length parameter simply means that the velocity vector has norm 1, right? So that's what this means. And now what I'm going to do is that I'm going to restrict that capital omega to L. And what do I get? I'll get Lx prime plus I Ly prime ds. Okay, so if you look at what this is, you can draw L prime, and you have here Lx prime, you have here Ly prime, and because it has unit norm, L prime has unit norm. If you look at this angle, let's call it beta L, between the x-axis and L prime, then Lx prime is cosine beta L, and Ly prime is sine beta L. And so this thing here is e to the I beta L. Okay, so what you find is that there is this function e to the I beta L from L to the circle inside C. And the condition that L be a straight line is the condition that it always makes the same angle, its velocity vector always makes the same angle with the x-axis. So it's the condition that this function be constant. And L is a straight line if and only if e to the I beta L is constant. So that's how you characterize, that's one way to characterize straight lines. So that the angle that they make, that their velocity vector makes with the x-axis is always constant. Okay, so beta L here, so here beta L is the angle that L prime makes with the x-axis mod 2 pi. So it need not be defined in general. What you have is just the exponential of phi times it. But in some cases, you can find the lifting of this function, and then it's just the up to summing or subtracting multiples of 2 pi. It's the angle that it makes with the x-axis. Okay, so that's how we characterize straight lines. And then the second thing that I want to tell you is how to deform an initial L naught to a straight line. Okay, so I'm going to draw again a picture here. Let's say we have an L naught like this. This is all supposed to be, anyway, it's supposed to have constant slope. It didn't quite work out. But, and we have this one. L naught is this one. And I want to define it to deform it to the straight line that is in white. So what we want to do is to find an LT, a one parameter family of Lagrangians, which evolve in time, but what do I need to do is to push them in the direction of their curvature. So this thing here is the curvature, which is the second derivative of LT, of L naught in this case, with respect to the arc length parameter. So that's the curvature. So I want to find a one parameter family of Lagrangians that are deformed along their curvature. So that means they evolve through this equation. So this is called the curve shortening flow. And in order to be able to deform L naught to a straight line, there is a necessary condition, which is that this function, I need to be able to deform this function to a constant. So So it needs to be homotopic to a constant, and that means that I can find a lift beta L naught from L naught to R. So that function must admit a lift beta L naught from L naught to R. Okay, so that's a condition. And under this hypothesis, then this LT evolving through the curve shortening flow exists for all time and converges to a straight line. So this is a result of, this follows from work of Gage and Hamilton in '86, plus the work of Grayson. The work of Grayson is what really proves this, and Gage and Hamilton set up the stage for Grayson's work. Okay, so this is one of the most important theorems in what's called the curve shortening flow. And it is this and that characterization of straight lines that I've mentioned there that I will generalize to higher dimensions. Before I go there, is there any question?
So sorry, so now you are going to also tell us what means Hamiltonian equivalence in general, right?
No, I'm not going to. I could do that, but it's not particularly.
Okay,
if
no.
you don't know it already, you would not understand it better. And I find that this example already explains more or less what it means.
Sorry, maybe here there are many people from PDEs. How does this PDE look like? I mean, if you're in one dimension, sorry, two dimensions.
That's right. Okay. So the PDE is written here. Sorry. The PDE is written here. LT here is the function from the circle to the two torus in this example. And the PDE is written here. It looks like, if you look at it, it looks like the heat equation, right? dt LT minus ds square LT equal to 0. But it is not linear. It is not the heat equation. It is not linear because S is the arc length parameter. So it depends on parameter of LT. So it is varying with time.
Okay, but it looks like this PDE is like these shrinking equations that engage old papers, right?
So it's a parabolic equation. It is, if you violate this condition, then it must admit a lift. So for example, if you pick an example where you start with an L naught that looks like this, say a closed curve, L naught, then what happens is that this will indeed shrink to a point. So it will never have self-intersections. It will get more rounds until it shrinks to a point. Okay, so this is another case. In the case where the L naught is not closed like that, it's not where there is such a lift. If there is such a lift, then it really does more or less what this picture here is showing. It is pulling it out in this direction and making it more straight.
Okay, but the evolution of LT along this equation has nothing to do with the Hamiltonian isotropy, right?
Okay, so that's an important question. So if this happens, this condition, then the evolution of this equation preserves the Hamiltonian isotopic class, meaning that the signed area between LT and LT prime will always be 0. So under this condition, LT and LT1 and LT2 are always Hamiltonian isotopic. Meaning that the area of the region DT1, T2 that is bounded by LT1 and LT2, so which boundary is always 0. But if this condition is violated, like in this example, it will not preserve the Hamiltonian isotopic class. Does that answer your question?
Yes, I mean, but is there any relation between this beta and the Hamiltonian inducing the flow? Or
there is indeed. So this ds square LT is going to be ds of beta LT. So basically, the beta LT is up to a constant ds LT, up to a constant. So then, exactly, yeah. Yeah, so these are all things that are very key in proving gauge Hamilton's and Grayson's results. Are there other questions?
Oh, there is nothing more. Go ahead.
Okay, so let's go to higher dimensions. So in higher dimensions, I will need not just the sympathetic structure, but what is called a Calabi-Yau manifold. So that requires a lot of extra structure, but it's not really necessary that you know what all this extra structure is, but basically this G is a metric, a Riemannian metric. This is a complex structure, and they satisfy some compatibility conditions and G needs to be actually Kahler and Ricci flat. And this omega is a complex valued n form on M. So analogous to the previous complex valued one form that we had, that was dz. And then an important point is that if L is Lagrangian and oriented, then you can consider omega restricted to L. And it turns out that this thing has norm 1. But you also have the volume form on L given by the induced metric. And that also has norm 1. But this is a real valued one form, and this is a complex valued one form. So they must be related by a unit complex number. And so they must be related by this. And so this defines for you a function from L to the circle. This is called the Lagrangian angle. And using this function, you can now define what is called the special Lagrangian. which is the analog of the straight lines, and they are defined by the condition that this function is constant. Okay, so this is the definition of a special Lagrangian. And they will be our candidates to be the best representatives of an Hamiltonian isotopic class. But now let me make a remark first, or an observation. So if you are given an L naught, so for it to be Hamiltonian isotopic to a special Lagrangian, you must be able to deform e to the I beta L naught to a constant. And if you are able to deform e to the I beta L naught to a constant, that means that e to the I beta L naught is homotopic to a constant. To a constant function. And so there exists a lift. In that case, there exists a lift beta L naught. Sorry, I should have written not like that. Beta L naught from L naught to R. And this is called a grading. And a Lagrangian together with a choice of grading is called the graded Lagrangian. So a choice of grading is just a lift of this Lagrangian angle map. And a graded Lagrangian is a Lagrangian together with the choice of this lift. So you can think of these as generalizing the notion of a straight line together with a function which tells you at each point the angle that the velocity vector makes with a fixed line up to 2 pi. So this is called the graded Lagrangian, and from now on, all Lagrangians are graded. From now on, all Lagrangians are graded. L is always compact. But M may be and will be, in fact, so I'll just write will be non-compact. Okay. So now a few questions arise. So the first one is, given L, an Hamiltonian isotopic class, does a special Lagrangian, I'll write special Lagrangian just like that, exist? And then the second question is the analog of being able to deform to there. So if you are given L naught and a one parameter family of Lagrangians evolving through the analog of the curve shortening flow. So the analog is you take dt LT, and that is equal to not the curvature, but what is called the mean curvature. So that's the analog of what the curvature was in the case of curves. So this is called the Lagrangian mean curvature flow. And the question is, does this family exists for all time and converge to a special Lagrangian? Okay, so these are two questions, and there are two conjectures on these, and these are based on a phenomenon called mirror symmetry, and these are conjectures due to Richard Thomas and Yau. And so the first conjecture, that's Thomas, and it says that L admits a special Lagrangian representative if and only if it is stable. So stable is I'll define what stable is. So stable means that this Lagrangian Hamiltonian isotopic class cannot be decomposed. So there is as L1 connects sum L2. So this is the Lagrangian connect sum with the average grading of L1 greater than the average grading of L2. Okay, so this is motivated by mirror symmetry and based on what happens in what is called the mirror side. There is a notion of stability for holomorphic vector bundles on a Kahler manifold. And there the notion of stability means that there isn't no subsheaf whose slope, which is the analog of this average grading, is greater than the slope of the whole thing, but it can be translated into this condition here for so you can use that to motivate this conjecture. Okay, so this is the conjecture. And L not being able to be decomposed in this way means you cannot find the representative of this Hamiltonian isotopic class that is of this form. And then the conjecture on the other side, to answer the second question, that's due to Thomas and Yau. Is that, so I'll write the conjecture with a modification plus an extra hypothesis that is actually necessary, but they didn't write. But it was later understood by André Neves that this was a necessary hypothesis. Okay. So I'll just write which is necessary from the work of André Neves. Okay, so if L naught is flow stable, which is, you can think of it as being the same condition. In fact, Thomas and Yau just say stable again, but in fact, if you look closely, their notion of stability for the flow is slightly different, so I prefer to call it flow stable. So Jason Lotay and I introduced that nomenclature, flow stable, and almost calibrated. That's the thing that André Neves showed you need to at least have that. I'll say in a second what it means. Then the Lagrangian mean curvature flow, LT, starting at L naught, exists for all time and converges to the special Lagrangian from conjecture 1. Okay, so what does it mean flow state almost calibrated? Almost calibrated means that, remember, these are all graded Lagrangians. So you can look at the total variation of the Lagrangian angle. And this is the requirement that this be less than pi. So if you think in the case of curves, where beta L naught is the angle with a fixed line, then this means that the velocity vector takes values in a half space. So something like that. It never varies more than in a half space. Okay, so for example, this is okay, but something like this would be wrong, would not be okay. So if you do something like that, you see, because here it goes like that, here it goes like this, here it goes like this, here it goes like this. So here like that. So you see it already has a total variation of something like from here to here. So and all that is more than pi. So so you cannot have this one. I'll just cross it. This is not almost calibrated. Okay, and basically the idea is that if you started with something like that, it might be the danger that some component of it here, some neck that it has, will shrink and pinch off the rest. It doesn't happen for curves, but it happens in higher dimensions. That's what Andrenev showed. And then the results that I have to, maybe before I go there, is there any question? I'll pause here for questions.
Yes, I mean, I would like to, as you said that this omega n form is closed, right?
This n form here, yes.
The omega is closed. So it induces a sort of calibration or something like that?
Yes, it is a calibration. So I didn't mention that, but I should have. So these special Lagrangians, they are calibrated. So they are.
So if you think of the Grassmannian, right? Where you see the tangent vector fields to these Lagrangian submanifolds. I mean, are they real? Are they complex? I mean, the vector fields, the n vector fields calibrated by this form locally?
They are real.
And what is the difference between the Lagrangian and the special Lagrangian vector fields then? N vector fields.
So Lagrangian is a much more flabby condition. Being special Lagrangian is much more restrictive. Lagrangians are not calibrated. The special Lagrangians they are calibrated, and they are calibrated with respect to, so if they have this angle there, they are calibrated with respect to e to the minus I b eta l omega, and you now take the real part of this. So the real part of that.
And if you insist in making like this geometric measure theory or whatever, are special Lagrangians volume minimizing in this Hamiltonian isotropic class or something like that?
So being calibrated implies that they minimize volume in their homology class. It's even better than in the Hamiltonian isotopic class. They minimize.
That's equivalent to that, right? I mean, special Lagrangian. So you should. So this flow should be minimizing the volume in some sense, right?
Oh, this Lagrangian mean curvature flow. It's actually the negative gradient flow of the volume functional. So, and that shrinks volume. And the idea is to try and use that flow to try and minimize the special Lagrangians.
But this is a mean curvature flow in codimension n, so it's much more difficult.
Yes, that's right. It's not a hypersurface mean curvature flow. It is a higher codimension mean curvature flow. So you don't have the maximum principle, for example.
I see. Thank you.
You're welcome. Okay, so the results that Jason Lotay and I have.
I'm sorry. Sorry, I just wanted to ask, what does it mean flow stable?
It's similar. It's similar to this. So you cannot decompose it in this way. And also there is a further condition, which is that the volume of L naught, every time you decompose it in some way, even if it's with a less here or a less or equal, then the volume of L naught is less than the sum of the volumes of the two components. Okay, so there is an extra condition. It's basically this, so maybe I'll do it like that. So flow stable is this plus if L naught is Hamiltonian isotopic to this, then the volume of L naught is strictly less than the volume of L1 plus the volume of L2.
So in general, you could expect that is smaller or equal, or that it's equal, for example, right?
What's the volume of this average grading? The average grading could be equal, that would be fine.
But can it be larger? I mean, can I expect any inequality in general, in the most general, without other hypotheses? Or is
you can construct examples with almost everything happens.
Everything, okay.
Then you might not be able to show, for example, that the flow exists for all time.
Yeah. Yeah. Okay. Okay. Thanks.
Yeah. So the idea of adding this is that prevents L0. So this prevents L0 breaking itself into L1 and L2, because the volume of L0 is already smaller than the sum of the volumes. And so because the mean curvature flow shrinks volume, it cannot happen that you are decomposing L0 into L1 and L2. That's basically what this extra condition imposes. And that's where it helps you.
And they are independent in a way, right? So flow
yes,
stable.
I could construct examples of L0 which are stable, they are not flow stable. It's easy to construct those examples.
And almost calibration.
And almost calibrated, yes.
They are also independent.
Yes, yes.
Mm-hmm.
Yes, I can construct examples of things that are almost calibrated and stable, but are not flow stable.
Okay.
It's relatively easy to do, in fact. So, in those examples, I would not know if the Lagrangian mean curvature flow really exists for all time. I can probably find examples where I bet 99% that it does, and the examples where I bet 99% where it doesn't, but I wouldn't be able to prove anything about them, probably. So this is really a condition that really helps a lot in the analysis. So our results is we consider 4 dimensions with circle symmetry. So meaning that there is a circle acting and preserves all the structure. Then L is Hamiltonian isotopic through circle invariant Lagrangians to a special Lagrangian, if and only if L is S1 stable, which means it cannot be destabilized by circle invariant configurations. So this is basically a circle invariant version of this first conjecture. So I'll just say again what the left-hand side means and what the right-hand side means. So this means that L is Hamiltonian isotopic to a special Lagrangian through S1 invariant, circle invariant Hamiltonians. And the right-hand side means that L cannot be destabilized by a circle invariant configuration. Okay, so that's the first theorem. And then the second theorem says that, so again by Jason Lotay and myself, says that M as before, and L0 with circle symmetry, flow stable, and almost calibrated. Then LT, evolving through Lagrangian mean curvature flow, exists for all time and converges to the special Lagrangian from theorem 1. Okay, so basically these are circle invariant versions in dimension 4 of the Thomas and the Thomas-Yau conjecture. Okay, so are there any questions?
Yes, may I ask you, if you take the quotient by the circle action of the same 4, you get a free manifold, right? Or I'm wrong.
Right.
Or before, so what? Yes?
It's R3.
Okay, so which what would be the quotient of M4 with S1? Which examples do you have? I mean, what do you get? Because you have a Richard.
Can you say again? Can you say again? I'm sorry. What would be the quotient of what?
Of M4.
That's R3. Of M4 is R3.
Sorry.
R3. Euclidean space.
So okay, so M4 is not compact, right? No.
It's not compact. That's right.
Okay, I see. Okay.
But the L's are.
Sorry.
But the L's are the Lagrangians.
There is no compact example of this.
The Lagrangians are compact.
But M4 is never compact. Or the
M4 is always non-compact. There is no compact example of this.
Okay, I see.
Basically because they are Ricci flat and they have a full holonomy SU2. So that means that if they would be compact, then there would be this circle would generate for you a killing vector field that would split off one direction, and so there would be a product of a 3-dimension of something that is 3-dimensional with something that is 1-dimensional.
Okay, so you're saying that there is no fibering over a compact manifold that gives you a Kahler manifold.
Yes, I'm saying that this condition here implies that they are non-compact. That's what I'm saying.
Okay, yeah, okay. So you have to work a little bit, and that's good. Okay, obviously.
Yeah.
So I have also a question. L0 in the second theorem, is the same as this the L that is mentioned in the previous theorem, right? You suppose that furthermore it's stable and the other properties, right?
Yes.
Yeah, okay.
Yes, but the first theorem applies with a little bit more generality because you don't need to require L0 to be almost calibrated and stable, and so stable.
Yeah, okay, thanks.
Yeah.
Excuse me, is omega in your examples exact?
You are asking if you are asking if little omega is exact, d of something.
Yeah, I mean, this is because you have this non-compact guy, so
it is not always the case, but there are many examples where this is the case.
Okay.
But not in all examples. So I can say quickly, how much time do I have? I can quickly explain. Yeah,
go ahead. I mean, I think Marielle couldn't stay for longer because she had another talk, but yeah, go ahead. Okay. It will be recorded anyway.
If you give me 10-15 minutes, I can say some words about the proof, and that might answer some of the questions.
Yeah, sure.
Okay, so how do you go about proving this? So let me call that 4. So the first thing is that the circle symmetry tells you that you have a map from M to the quotient which is R3 in this case. I call this mu. So maybe I'll draw this here. You have M to R3. This is mu. I'll draw R3 like that. Okay, and this is actually if you are familiar with it, this is the hyperKahler moment map, because these Calabi-Yaus in 4 dimensions are the same as being hyperKahler, and mu is the hyperKahler moment map for the circle action. And this has the property that there exists a finite set. It's actually a discrete set, but let's suppose it is finite. For M to a finite topology, it needs to be finite. A finite set S such that if you pick a point in this set, the preimage is a point. If you pick a point that is not in this set, then the preimage is a circle. Okay, so let me draw the points of this set. It can be here. Okay, let's suppose that these are the points of the set. Yes. And if I pick a point P that is in the set, let's say this one, then the preimage is a point. If I pick this one, for example, then the preimage is also a point. But if I pick any other point, let's say one of these, point here, then the preimage is a circle. Okay, and now the question is, okay, so what is a circle invariant surface? That's the preimage of a curve in gamma, a curve in R3. So L, let me say it like that. L inside M is S1 invariant if and only if L is the preimage of a curve. So, and then, for example, you can pick as a curve some line connecting 2 points, 2 of these points. Then above each point of this line, you have a circle, right? You have it here, you have this circle. But if you are here, then you also have a circle. If you are here, then you also have a circle. But these circles collapse at the endpoints. And so the preimage in this case would be a two-sphere. Let me draw it nicer. So you have a family of circles that at the end collapse to a point, and that's a sphere. Another example would be for you to pick, let's say, if you pick a simple closed curve downstairs, then above you have a circle above every point. So in the end, you have a two torus. It's not very nice drawn. Okay, so that's a two torus. Okay, so, and then what does it mean for L2 to be Lagrangian? That's equivalent to gamma being planar. Planar means it lies in a plane, and without loss of generality, you can suppose it is perpendicular, lies in a plane perpendicular to the z-axis. So lies in an R2, okay? Okay, and then beta L, if L, so L is mu minus 1 of gamma, and then beta L is equal to the angle that gamma prime makes with the x-axis, mod 2 pi. So just like in the example that I had first given. And so using this now, you know what it means for L to be a special Lagrangian. That's equivalent to beta L being constant, but that means that gamma is a straight line. Okay, so now we know what circle invariant Lagrangians are and circle invariant special Lagrangians are. And now we need to understand what it means for two Lagrangians to be Hamiltonian isotopic. So what does it mean for mu minus 1 of gamma 1, let me say gamma 1, yeah, to be Hamiltonian isotopic to mu minus 1 of gamma 2. This is equivalent to you being able to isotope gamma 1 to gamma 2 through planar curves which do not intersect those points of S. So gamma 1 and gamma 2 are planarly isotopic, not crossing S. So remember, S is these points here, right? S is this discrete set of points, okay, above which this vibration, the fibers of this vibration are points and not circles.
So for example, it could be that the plane where they lie doesn't contain any point in S. It could happen.
It could happen if you have, for example, a curve that looks like this yellow one.
Mm-hmm.
But it turns out that for you to be able to have a grading,
mm-hmm.
so the condition that you can find this grading means that the endpoints of the curve always need to be points of S.
Okay.
So you will always have to pick planes that contain these points.
Yeah. Mm-hmm.
By the way, and these points and the number of points and their position, you can pick them as you wish, and that will give you different examples of Calabi-Yau manifolds in this case. So those are free to choose, and that will give you different examples. Okay, so let's see here an example, or just to make sure we understand. So let's suppose we have 3 points in S, and they are in this plane. And I have some Lagrangians that are straight lines. Say I have this one, call it L1. So these are curves that correspond to Lagrangians upstairs, L2. And I have L. So of course, mu minus 1 of these Li's, I'll call this L0 maybe, are special Lagrangians for I equals 0, 1, 2. And now I'm going to consider some other Lagrangians. I'm going to consider, call this gamma 2, this curve gamma 2, and I'm going to pick another curve gamma 1, like here. And of course, mu minus 1 of gamma 1 is Hamiltonian isotopic to mu minus 1 of L0, because you can simply deform gamma 1 to L0 without crossing any point of S. Just follow that arrow that I've drawn. But mu minus 1 of gamma 1 is not Hamiltonian isotopic to mu minus 1 of gamma 2, because to Hamiltonian isotope gamma 2 to gamma 1, you would have to cross that point there, and you can't. That's forbidden. Okay, that's forbidden by these conditions here. Okay, so is this clear, this example?
Yeah.
And so, but what happens, let's say you really try to deform gamma 2 to L0, if you really want to do this. What happens? What happens is that as you deform gamma 2, so I'm going to draw again the points. As you deform L2, gamma 2, you will be stuck here around this point. You can't cross that point. So you are deforming gamma 2, mu minus 1 of gamma 2, into something that is the connect sum of L1 of mu minus 1 of L1 and mu minus 1 of L2. So this is basically, you are showing that mu minus 1 of gamma 2 was unstable in a way. And you can check really this is unstable, because if you look at what the average grading of this guy and what the average grading of that guy is, it's basically these angles here. This is the beta L1, and the beta L2 is this thing here. So this one is positive and this one is negative. So in particular, here beta L1 is greater than beta L2, and this destabilizes mu minus 1 of gamma 2. So and once you understand this picture, what makes something unstable and how it can be destabilized, it's not very easy to put on a proof of the first theorem. So the first theorem really does not require any heavy machinery. It just requires understanding this picture that I've drawn, and then basically the logic will lead you to the proof. Now, the second result requires a little bit more of, requires some analysis. So let's take a one parameter family of circle invariant Lagrangians evolving through Lagrangian mean curvature flow. Then this is equivalent to gamma t evolving through a modified curve shortening flow. And once you have that, then the grading evolves through the heat equation. So its total variation in particular is non-increasing, so it remains almost calibrated. So sup beta t minus inf beta t is less than what it was at t equal to 0. Less or equal, which is then less than pi, and so LT remains almost calibrated. And then through the classification of ancient solutions to the Lagrangian mean curvature flow. That's a recent not really ancient, not all ancient solutions, of almost calibrated ancient solutions. That's work of Lambert, Lotay, my collaborator, and Schulz. We find that for LT to develop a finite time singularity, then gamma t must cross or must hit a point of S of that discrete set. But that would destabilize gamma. That would destabilize LT, and so is impossible because you are assuming this flow stability. Remember, so this means that no finite time. Maybe I'll go here. No finite time singularity. And LT exists for all time. And then a standard argument shows you that it converges to the special Lagrangian from the first theorem. So gamma t is converging to a straight line. Gamma t converges to a straight line. Okay, so basically this is a sketch of the proof, at least how it goes logically. And I'll stay here, and thank you for your attention.
Okay, thank you very much, Gonzalo.
Thank you.
I think it was very clear. It's very nicely explained. Are there any questions?
Maybe you said that, or it's obvious. The singular set S is how do you say, is dimension 0. It's obvious that it's dimension 0, or it was just a picture that you make. I mean,
no, it's not obvious. This comes from when you look at these Calabi-Yau for manifolds with circle symmetry. Then if you want the metric to be complete and the holonomy to be irreducible, then it turns out that you need to have S to be non-empty and be discrete. You could construct using, so this is what is called the Gibbons-Hocking ansatz. to construct these metrics, but in fact, all these Calabi-Yau metrics with circle symmetry come from this construction. And you could try to construct examples where this singular set, this S, is not discrete, but it's like a curve. But the resulting metrics will never be complete.
I see.
So basically, what the input you need is to construct this metric is an harmonic function on R3. And for it to be at least complete at infinity, you need it to be bounded, okay? But there are no bounded harmonic functions on R3 that are non-constant. So what you need to do is to introduce some singularities. And you can introduce singularities at points by using the Green's function based at those points. It's as if you were putting electric charges at those points. But you can also solve the Poisson equation with electric charges that are not at points, but let's say along a wire. But it turns out that the metrics that result from those harmonic functions will never be complete. Because because they will cross zero. Basically, that's the problem. They cannot be bounded by above or below. They will be unbounded in both directions, and they will cross zero. And because you need to use that function in the metric, that will make the metric degenerate somewhere.
And the other thing that you mentioned that nu was a moment map. Right. Or you said that, right?
That's right, yeah.
Which is the role of the moment map here? I mean, the R3 you're considering as being the Lie algebra of what?
Well, so the R3 is not the Lie algebra of S1 is R, but you have 3 moment maps because you have 3 Kahler forms. So
you said this hyperKahler thing that you mentioned,
copies
right?
Of the Lie algebra of S1, which is R.
Because of this hyperKahler thing that you said at some point, right?
That's right, that's right.
Okay, I see, yeah, thank you.
Yeah, you're welcome.
Okay, I see. I see. I think I have something to learn here because the ZX is playing a special role in a way in this representation of.
Well, no, it's not so important. You can rotate everything, and so there is no loss of generality in pretending things are perpendicular to the z-axis, because if you want another axis, you can just rotate the hyperKahler structure, and that rotates also R3.
Okay.
So there is no loss of generality in this. Everything is supposed to be SO3 symmetric.
Okay. Well, I think it's So are there more questions? If not, well, thank you very much for coming. It was very interesting.
Thank you for the invitation and the questions there. You asked very nice questions.
Yeah, especially Daniel Pons here.
Yes. Interesting questions.
Okay, so